but we'll see. I'm going to talk about Lebesgue, so I looked up Lebesgue, and what's interesting to me is he's post the era of the PDE guys, Fourier and D'Alembert, all those guys, and the Euler, all that stuff. He's right past that. It's almost like that traction from all the grand results people were coming up with during the French Revolution and shortly after was followed up by the work of Lebesgue and a few others. And really, the theory behind PDEs was really built in from this era to the 1950s. So it's not that old. In fact, I'm still going to bring in that book someday where that Paul Hamels has taken pictures of people. You see Sobolev and all these individuals who are responsible for developing the theory of differential equations. They're in the book. So cameras were developed and they actually have pictures of these people. So 1941, that's not really that long ago. So his father was a printer, and he first studied at a college and it wasn't that great of a college. And later he went to Paris, where he studied at Lycée in St. Louis, and he entered École Normale Supérieure, and he got a teaching math diploma. So I guess that must be their version of math ed. He studied in the library, and he studied Bayer's work. Bayer is known for topology, actually. That's what I know him for, the Bayer category theorem, which I don't think you would get in a topology course here, because you probably do point set. I learned it in measure theory. So he was extending the work of Bayer when he first started in mathematics. He built measure theory. He developed an entire field of measure theory, expanding the work of another individual named Borel, who also was at Lycée in a landmark 1901 paper. And I have this paper. It's actually on JSTOR. You can look it up. It's there. You can print it out. What this work was about was generalizing the Riemann integral. And in fact, when you take measure theory, one of the first things they show you is why the Riemann integral has flaws, and they show you some examples. These examples that you see, they seem contrived. Like they'll show you examples where Riemann integration fails, and you have to come up with another way of integrating, and they'll show you Lebesgue integration, but these examples they show you are kind of really contrived. But I think the real thing about Lebesgue integration, it's the right way to think. It's a very general way to think. He actually did fall out with Bayer over who had the right to teach. This is a special lecture that they were invited to, and they wanted to decide who was actually had the right to teach that lecture. So it was like a research lecture. In fact, his work on measure theory was not well received by the classical analysts at the time. But really, when you see his work being laid out, he revolutionized analysis the way we know it. Lebesgue cleaned up the theory of Fourier's theory. Fourier made some assumptions about when you could expand something as a trig series, and he assumed something. In fact, every time we looked at those series, you probably heard me say, "Ah," when I was swapping the integral and the sum. He made some assumptions of when you can do that, and his assumptions are actually not quite true. So Lebesgue was the one who tightened up that theory and told you when you could swap those limits, because the series is a limit and the integral is also a limit. If you make the assumption Fourier made, then you can prove that if a function can be represented by a trig series, then that trig series must be Fourier. So Fourier did the groundwork, but he had an assumption that was flawed inside there, and Lebesgue cleaned it up. So his assumption wasn't always true. So if you change the notion of integral from Riemann to Lebesgue, that assumption does become true. So it's cleaning up this assumption that kind of, I think, generated Lebesgue integrals. I'm just going to do one little bit more in infinitesimal transformations, and then I'm going to move on off of that. Well, maybe I won't do this. Let's see. We can go back to it if we want. Let me tell you a little bit, okay, of the summary. I won't go through the calculations again. But the whole idea of doing this generator, or this infinitesimal generator, this going by a little bit, is that if you repeat this repeatedly over and over, apply this group over and over, this process, what you're going to get is a curve. And that path that you're going to get turns out to be the integral surface that we first learned about at the beginning of the semester. So it's like the theory of the characteristics that we did back at the beginning of the semester. That's where it's going to. This path that you're going to get when you apply this generator over, so it's the transformation. When you keep applying this transformation in little pieces at a time, you get a path and a path, and that path turns out to be the integral curve of these two differential equations, which you know where they came from. They came from a PDE to begin with. So that's the theory doesn't remove the messiness of the calculations, as you saw probably from your work on the exam 2. It's messy still. It just gives us the structure and allows for an exhaustive search of what's going to be invariant or not. So Ryan was asking, how do you know? It seems like magic that this comes. It's not, actually. You're setting those parameters up in such a way that you're guaranteed invariance, and you're solving for those parameters. So you can actually solve for all possible cases of those parameters and generate the entire invariant group. And there were books at the time where they did that for one PDE after the other. So there's a lot of messy calculations. And in fact, I feel like one of the first pieces of software, that computer algebra software, would do that for you. Like you could actually put it in there and it would do it for you, calculate the group, the invariant group. So if you want to go back to that, we can. It's and I can go through that more carefully. But I really want to move on to semigroups of linear operators, because I think this might be a good place to end. Can everybody hear me?
Yeah.
All right. So to do that, I have to give you some definitions. The first is a Banach space. Banach is actually a Polish mathematician. And X is called a Banach space if X is a normed vector space over a field. You can take that field to be R, but if you're inclined to like algebra, you can take it to be Z2. So it can be any field. And just to remind you what a norm is an abstraction of the absolute value to other vector spaces. Absolute value is a measure of size on R. Here we have just an arbitrary vector space. The norm has a first property that absolute value has is that it's always non-negative, and the only way that you can get that value to be 0 is if the inside is 0. So that's a nice property of absolute value that's been abstracted. The second is that if you have a scalar that came from the field, that scalar can come out as an absolute value, so you can scale out things. And finally, the most difficult usually to prove in an advanced calc class is a triangle problem, right? You always leave that one for last. And what is a vector space? It's those 8 properties that you got in linear algebra. I'm sure you had to memorize the definition of a vector space. So it's closed under addition, it's closed under scalar multiplication, it has a 0 in it, so it has all these properties. In fact, I've got this fantastic set of books where they describe a vector space in terms of a group and a ring. Didn't we do that in abstract algebra? We did that at the end of abstract algebra. I said you can actually define a vector space. Yep. Something's a Banach space if it is a norm vector space over a field that is complete. Complete means that all Cauchy sequences must converge in that norm. So the definition of Cauchy sequence is that if I have a sequence in the vector space, so you can think this vector space, you probably have a lot of familiarity with the vector space being R and even Rn. But now you want to think of that vector space as actually having functions in them. So xn could be an entire function. So the function's converging in a norm to another. If we know that the functions are getting close to each other in the norm, then this series converges, and its limit must be in the space. So I think we talked about that in abstract algebra too. The idea of what it means to be complete in the sense of algebra means that you have to contain all the roots, and what it means to be complete in the sense of analysis means that you've got to contain all the limits. just to remind you, what we mean by convergence is that a sequence converges if to X, if for every epsilon greater than 0 there exists a capital N, such that you go far out enough in the sequence that all those members can be squished down below epsilon.
Is that why we're doing this over the reals and not just like the rationals?
Right, exactly. The rationals is not a complete Banach space. It's a vector space, but it's not a vector space, right? Unless you define the field to be something else, right? Because you can't, if your field is R, it's not a vector space because it's not closed under scalar multiplication. So what would a norm vector space look like that's not complete? You can take your field to be Q, and then it's not, and you can take the absolute value to be the norm. Everything's fine and dandy, but there's many Cauchy sequences that don't converge. For example, that's a completely a sequence of rational terms, and it doesn't converge in Q. It converges to E. So it's like we talked about in abstract algebra, closing up the set so that we have all the good properties in there. So in terms of analysis, closing up your set means that you're closing up by all the limits. You're making sure that it's got complete closure when you take a limit. Closing up in the sense of modern algebra is you want to close up under taking roots. And we talked about the very cool thing that R is a field that you can only get by closing up by limits, right? Because when you try to close up by counting in all the roots, you get C, you don't get R. And I think I went to Dr. Lee. Extension fields, like the extension field that you will get when you start taking one root is like square root of 2 is you get all of C, right? But you won't get R by doing that little manipulation. R can only be generated by closing up the limits on the rationals. So R is an analysis animal, and C is an algebra animal. So if you close up by all the limits, you'll have R. Remember, R is not algebraically closed. It's because it doesn't contain all its roots. So you can create polynomials with coefficients in that field that do not have roots in that field. So it's not algebraically closed. For that, you need C. And C, by the way, is a Banach space under magnitude. And it's isomorphic to R2. So do you want me to back up so you get these definitions in there? Just tell me how far to back up. Yeah, so you can write it this way.
Create a polynomial with rational coefficients. All the solutions have to, you can't get all solutions without extending. And the way we introduce it is we start with just the fact what we would call extension fields, where you take one and you need to add this element to complete the field, but then because it's to be a field, it has to have all the inverses of that element, all the linear combinations of that element, and it just expands all the way up to C.
And so what we realized when we were teaching the modern classes, or the abstract algebra classes, there is no way that you can get R as an extension field of another field. And that's pretty cool. Good? So what's a semigroup of a bounded linear operator? Well, I needed to back up a little bit to give you some pre-definitions. A bounded linear operator, well, first, if X is a Banach space, and I have a one-parameter family, that means for every little t, I get an operator. So an operator like you had in Dr. Solon's class. And they go from X to X. It's going to be a semigroup if it satisfies property 1 and 2. It's not a full-on group because what is it missing?
Inverses.
Inverses. So you have solutions backward in time. And I is the identity operator. So that's why we call it semigroup. It only has half the group. So I'm going to define what I mean by bounded in a second. But sometimes I wonder if I have left the field of math completely. And then when I go through notes like this, I realize there's no way. There's no way. I love this stuff. It's composed. So they're operators, right? So you're composing them. So your binary operations composition. And in fact, I think at some point in modern algebra, most of our structures that we set up had something to do with composition at some point or other. I feel like that. Starting off with permutations.
What's that called again where the inside operation equates the outside operation homework? That's no.
Is that right? Homomorphism? So first, to tell you what a bounded operator is, I have to give you the definition of operator norm. So if you have a vector space that's normed, the vector space has a norm on it, so you have a notion of distance. Then let's suppose I have a function, an operator, that takes elements. So the inputs of this operator are elements in the norm vector space, and the outputs are norm vector space. And we say that this operator, and I put the t here, but in general, it doesn't have to have a t. I just put it here to put it in context of what we're doing. We say that this t of t is continuous or bounded. It's the same thing. If I can find a c such that this is true for all x's. We call this t of t a bounded operator for one fixed t. Or we call it also a continuous operator. Same thing. I mean, it's the same word. It's interchange. They mean, it's the same word. The operator norm, so if you remove the x's here, that means that the norm that you have on this operator is not going to be a function of x anymore. Right over here, all your calculations are a function of x. But if I take the minimum of all the possible c's that work, like if I find one c that works, it's not necessarily the minimum of all the c's that work, right? But there's only one minimum. So take the minimum of all the c's that work for this inequality up here, and that c is called the operator norm. I'm probably going to say this wrong, but for normal matrices, those are matrices where A transpose is equal to A transpose A, and they're square. It turns out that the operator norm is the absolute value of the largest eigenvalue. Spook. So note that I put t of t in to keep it in context of what we're doing. But if you had it in a regular linear operator theory class, you would not have t of t, you would have A, just one. If we have a family of them, so I'm keeping it all family in the definition so that it makes sense. In general, if I have a linear operator, what I mean by it being bounded is all of this stuff. It's called, and that's called the operator norm. We say that a semigroup of bounded linear operators, that means for each t of t is a bounded linear operator. It's going to be uniformly continuous if the limit of t goes down to 0 from the right of t of t minus I is equal to 0 in the operator norm. So now I'm taking the minimum of all those c's every time, and that has to go to 0. Good? These definitions all seem like they make sense until you actually go compute something by hand. You're working on not real numbers. You're working on entire spaces of functions, and then operating on those functions. So you're actually taking a function and transforming it to another function. So when you actually go to compute these things, they become actually pretty hard. The linear operator that becomes this limit is called the infinitesimal generator of that semigroup. And you've seen this limit before. It's a differential difference operator. So it's the derivative of all of those T of T's as a function of T at T equals 0. That's what it is.
And then T goes down there, T of T, so X function is not
X, because T operates on X, right?
the X.
That's
It almost looks like it cancels out less than zero.
Yeah.
evaluated at T equals 0.
No, no, right below that. It's on the next
Oh,
line.
yeah, sometimes when I write something like that,
Yes, right.
yes, it's yes. And this A, you're not working with reals. So this is an operator. So whenever this limit may not exist for every single x, it may only exist for some of the x's. So the x's that it exists for is the domain of that new operator where you can compute that by taking the limit. And that particular operator is called the infinitesimal generator of that semigroup. I told you it's wild. The bulk of this comes from a book called Pazy. P-A-Z-Y is the author's name. But when I read it, it was like probably the main book in the area, and it's online completely free right now. I found a PDF. I have a hard copy somewhere, but people have done much better jobs since that time. So the books, it's funny because the books at the level we were one step ago, they're not very good, but the books at the next level are much better. dA is the domain of A.
The T of T, what would we do about the parameter itself? Like,
Hang on one second. You're going to see it in context with a
okay, yeah.
PDE. I'm going to show it to you.